Hello, welcome everyone. Today we're going to talk about how you can perform machine learning with Telegraf and the Execd processor plugin. More specifically, we're going to look at how we can create forecasts on temperature data for a home brew. My name is Anais Dotis-Georgiou, and I'm a developer advocate at InfluxData, and I've been with Influx for about 2 years. And joining me today is Steven Soroka, who is a senior engineer on the Telegraf team. So on the right-hand side here, we have InfluxDB v2 OSS running. And you can see that we have some temperature data coming in, and that's the orange line. And we're creating two forecasts, the purple and blue lines. And then we're also looking at the difference between our forecasts and our actual temperatures. And we are recording those differences there in an effort to find anomalies in our data. So before we begin and discuss how it is that we're producing these forecasts and these anomalies, I just want to give a brief overview about what Telegraf is. So if you're not familiar with InfluxData and InfluxData stack, there are two components to 2.0. And the first is InfluxDB, which is not only the time series database, but it's also a visualization and query and task engine. And then alongside InfluxDB, we have Telegraf. And Telegraf is an agent for collecting and reporting both metrics and events. You can collect data from a variety of different sources with Telegraf. You can pull data from Kubernetes, from other databases or data stores, from any applications and your network, et cetera. And then you can send that data to InfluxDB or any other database if you're choosing. Telegraf is plugin driven. And so this amount of flexibility is given to you by the vast number of plugins that Telegraf has. And some of these in plugins include input plugins, which specify where you're gathering data from, output plugins, which specify where you want to send data to. And there's also processor plugins, which allow you to process the data as you get it. And for example, maybe drop tags or rename tags and other such things. And then you also have aggregators, which allow you to, for example, find basic stats about your data and share those statistics and write those statistics to your InfluxDB instance simultaneously. There are also serializers, and all of these categories of plugins, there's over 200 plugins right now. And another really cool thing about Telegraf is that it has an incredibly active community. So out of those 200 plugins, I would say about 80% of them have actually been contributed to by the community. So if you ever decide that you want to use Telegraf, you are sure to find a lot of support either from the community team at InfluxDB or also the Telegraf team or also just other community members. And finally, some other nice things about Telegraf is that you can install it as a single binary. So it's really easy to get up and running with it. And finally, it's extensible in any language. And this last part will go into extra detail. And today you'll see examples of how we can extend the capabilities of Telegraf by incorporating Python script. So here's a really simple example of a Telegraf configuration if you've never used Telegraf before. So the Telegraf configuration is a TOML configuration, and with it, you can specify the configuration options for the agent itself, things like at what interval you want to collect data from, which in this case will collect data at a 1-second interval, or maybe also, for example, how often you want to flush that data to the output of your choosing. And in this case, we're going to flush data at a 10-second interval. And then you also might want to, for example, omit hostname to reduce series cardinality in your data. Then you want to specify where you're gathering your data from. And so you could use, for example, the inputs plugin, the CPU plugin, to gather stats about your CPU. And then I'm going to send these stats to an InfluxDB v2 version running on localhost. And I need to supply some other credentials, which include my token, the organization that I want to write the data to, and within that organization, which bucket I want to put my data to. And if you've never If you're unfamiliar with InfluxDB v2, I just wanted to show you where you can find all of these credentials. So if we look at the UI here, if we look under my profile, we can see that underneath my name, there is a org listed, and I've just titled it my org. And then under data, you can both create buckets and also Telegraf configurations, and also create or generate any tokens you need.
Okay, so I'm going to give you a little bit of an overview on the Execd processor plugin. It's one of a family of Execd plugins. There's the input, the processor, and the output. And these plugins let you run external programs and use them to extend Telegraf as if they were plugins. So basically, you start up an external process and you pass metrics back and forth with that process and between that process and Telegraf. And you do that by reading and writing line protocol over standard in and standard out for the process. So the process gets started up once, it stays running in the background like a daemon process, which is where the D in the name comes from. And it has a read loop that continuously reads from standard in, processes the metrics, does something with it, and then typically you'll serialize it back to line protocol and write it back over standard out. And this can be done in any language, not just Go. And today we're using Python because it's got really great machine learning libraries available. So yeah, this is what the process looks like. You know, Telegraf on the left here has a bunch of plugins running. So it's got input plugins, processor plugins, output plugins, and we're using the Execd plugin, and that's going to communicate with our external application. So we wrote an application in Python, which we'll show you, and it's standalone. So Telegraf is going to start that up as a separate process. And the Python application is going to read in from standard in, parse the metric, do something with it, and then write the changed metric back out to standard out. And all that communication happens in line protocol. So if you've never seen line protocol before, or if you want a refresher, it's a pretty simple text format. If you're not doing anything complex, you might not need a specialized parser or serializer. In our case, we actually just wrote out the text that we wanted directly to standard out. So it looks like this. The metric name is on the left-hand side here, and ours is temperature, and then followed by a comma and a list of comma-separated tags. And so the tags have a label and a value. So our label here is the brew that we're monitoring, and what the name of the brew is. And then that's followed by a space and a comma-separated list of fields. And the fields are the values that you're monitoring, that you're recording. So in our case, the temperature in this case was 21.2 degrees. And so that's our label and value for the field. And the tag values have to be strings, but the field values can be floats, integers, strings, booleans. It's more flexible. And then optionally, you follow that by a timestamp, which is the number of nanoseconds since 1970. So sort of like a Unix timestamp, but more digits. So this is our simple example of an Execd processor plugin, what this would look like if you configured it in Telegraf. On the top here, you have the processors.execd name of the plugin, and then the configuration for it. You have to tell it what command you want it to run. So in our case, we're running Python, and we're going to ask it to run our forecasting script. And a trimmed down version of maybe a starting point for a Python script might look something like the bottom section here. It has a read loop, which reads a line in from standard in. And the simplest thing you could do is print it right back out to standard out. And that would be a simple plugin that does nothing. What are we trying to accomplish today? We have two batches of beer that we are trying to make some sense of the temperature data from. One of them is called Haze version 5 and the other is called BV1. And the goal here is in brewing a beer is you want to keep the temperature in the early stages between 18 and 21 degrees. And so our friend Luke has donated some of this temperature data to us and shown us his setup. And we'll show you what that looks like. The objectives we want to add on to that is we want to forecast temperatures for the next 10 minutes going forward into the future. And we want to do some anomaly detection. So we want to look at the temperature data, see if there's any spikes in the data that don't make sense or that should require our attention. And possible reasons for this are, sudden changes in temperature maybe, but we're also seeing some misreads with the OCR technology we're using where it reads the temperature higher than it should be. And so that should trigger our anomaly detection and we can adjust the equipment or just make corrections to the data. So this is the brew setup. Following the arrows from left to right here, the first arrow is a Raspberry Pi that's running some OCR software. And that's hooked up to the second arrow here is a camera that is monitoring a digital temperature readout that's connected to the barrel here. And the last arrow in the right picture is a bucket of ice water. And our friend Luke would periodically refill this bucket with fresh ice to keep the temperature low. So part of this setup is notifying him that the temperature has gone too high and he needs to refill the bucket so that it comes back in line. And so that's it. This is what the digital temperature display looks like. The OCR that was being used is called 7-segment OCR, and he had this command running on the Raspberry Pi periodically that would take a snapshot from the camera, run it through the OCR, and try and make sense of that data before it's sent it on to Telegraf.
So before we get talking about how it is that we actually are implementing the forecasting with Python, I just wanted to take a step back to actually look at our data. So this is the complete data set, and we have two beers, as Steven mentioned, Haze version 5 and BV1. And while one of the beers, we continue monitoring it for an extended period of time, the monitoring period of interest is at the very beginning of the fermentation of these beers. And you'll notice that encapsulated by the white square here is the beginning of the brewing process and the beginning of the monitoring process. And you'll notice that the temperature fluctuates quite a bit. And so our goal here is to do two things: make sure that the temperature doesn't exceed 21 degrees, and then also we can minimize the fluctuations. So taking a closer look at the individual data, the first beer that we have is called Haze version 5. And the very first thing that you notice is that the timestamps are very close together. And that's because for this demo, we've compressed the time scale from 1 minute to 1 second. And we will be outputting forecasts for 10 seconds at a time, which would be equivalent to a 10-minute forecast, with the idea being that if we register an anomaly in that time, that then Luke has the opportunity or enough time to adjust his setup slightly to avoid fluctuations in temperature. And like we said, there's multiple reasons for why it is that we see high spikes in the temperature as well as drastic fluctuations. And one example of that is bad OCR reads. So you can see there that we have some temperature readings close to 29 degrees Celsius, which is really high and really sudden. Temperature data doesn't typically have profiles like that where it can suddenly jump up without any gradient. So we attribute that data to being bad OCR reads. And then you'll also notice that periodically, fairly regularly, but not entirely, there's not like a clear seasonality here or anything, but occasionally we have sudden drops in temperature data, and that's most likely due to Luke noticing that the temperature is climbing and either replenishing the ice, or perhaps the pump is being triggered to pump in more cold water. So this is what our second beer looks like, entitled BV1. And again, we see a fairly similar profile. It doesn't look like the data here, like we exhibit many bad OCR reads, but we definitely also have sudden decreases in temperature that we would like to hopefully minimize for Luke in the next time he decides to brew some beer. So given what this data looked like and the task at hand, we decided to use double exponential smoothing in order to create a forecast. And what is double exponential smoothing, or exponential smoothing in general? Well, it's essentially just an exponentially weighted average of the trend and the actual values of your data together. So what that means is that essentially the most recent trend values of your data and the most recent slopes will contribute the greatest to your forecast. And the reason why we selected this algorithm for forecasting was primarily because of just how little data is available to us prior to needing to detect anomalies and needing to generate forecasts. You can see that almost immediately we start to experience some fluctuations in temperature, and it's only maybe a couple hundred points in that we start to exhibit even more fluctuations in the case of Haze v5 version 5, and in BV1 we see these fluctuations almost immediately. So taking that into consideration, we know that we have to select an algorithm that doesn't require much training. That's the first consideration. And the second consideration is that both of these beers have a significantly different profile. And they also don't exhibit a very clear or well-defined seasonality. So this meant that we couldn't use some other approaches like ETS or REMA or Facebook Profit to create our forecast, because those methods require that you have clear seasonality. And then finally, we wanted to use a forecasting method that would be more flexible when dealing with a regular time series in case that we're missing values for whatever reason. So that's one reason why we selected to use exponential smoothing. And by the way, double exponential smoothing is also often referred to as Holt's exponential smoothing or Holt-Winters exponential smoothing. And that's because Holt-Winters, they actually developed what's known as triple exponential smoothing. If you take away the seasonality component from that equation, you're left with double exponential smoothing. And so oftentimes those two ways of describing the algorithm are used interchangeably. And so this leads me to a second point, which is if you're very familiar with InfluxData, you might know that built into Flux, there is a Holt-Winters function. And so you might be asking yourself, why would we bother implementing this forecast in a Python script with Execd when we could just use the Holt-Winters function in a task? And for me, there's two reasons. The first is that the Holt-Winters function in Flux isn't nearly as configurable as the stats model version, which is where we got our Holt's function from. And the second reason is that if you are new to InfluxData and you're new to InfluxDB, you might not feel comfortable or have the time to learn Flux and to learn how Flux's Holt-Winters function works. You might already be familiar with stats models. So another benefit to using Execd is just having the opportunity to work with the tools that you're already familiar with. And then I wanted to dive a little bit into some of the configuration options that the stats models library provided that made their Holt-Winters function a little bit more appealing to me. And the first element is that their version of Holt has a damped version available. So you can you can configure the fit method to include a damping parameter. And what this allows you to do is ensure that your forecast ends up meeting a saturation point, because Holt-Winters, as a result of it being a function that operates on essentially exponentially weighted averages, it has a tendency to approach like negative or positive infinity the further out you forecast. And so including a damped version allows you to sort of control the forecast. And therefore, when we go on to monitor the difference between our forecasted value and our actual value, we'll get a much more reasonable difference, much smaller difference. If we weren't to use the damped version, then we might frequently have anomalies that are on a really large scale, because all of a sudden the algorithm is detecting a peak in temperature and it just kind of runs away with this new transition in slope and like generates a really, really high forecast out into the future. So that was one reason. And then the other reason is we just wanted to take some time to compare different types of Holt's methods. So within stats models, you can not only specify whether or not you want the version to be damped or not, but also whether or not you want your trend forecast to be an exponentially weighted average or a linear weighted average. And there's some pros and cons to using both. And so I also wanted to describe that. I'll describe that in a little bit. And then the very last reason that we decided to use the Holt's exponential smoothing is also because it's extremely computationally efficient and very fast. So for example, here we are outputting 10 forecasts with every single metric being written. So at every 1 second interval. And we're fitting the data to 120 points every second as well. And it's able to handle this very easily. So this would, like, you could use this approach to forecast on several series, and that would be a great benefit. So now I want to take a second to talk about the code. But before I do that, I'm going to take a step back and describe exactly what we're seeing here in these graphs. I briefly introduced these earlier, but the orange is just our raw data, and the purple and blue here are our two forecasts. And there's the forecast regular, which is the normal Holt's forecast, which incorporates an exponentially weighted average of the trend. And then there's a forecast linear, which uses a linear forecast. And you'll notice that the linear one places more emphasis on his data. So it really does a better job of kind of representing the global trend, the more global trend that we see, or the larger trend that we see. Whereas a lot of times the exponential forecast, especially if there are these plateaus, it will just end up looking pretty linear. It's looking at the fact that the trend hasn't changed much in a long time. And you'll also notice that it keeps changing. And that's because every time that we get a value into standard in, we're creating a new forecast. And then out of curiosity, we wanted to see how it is that these two different algorithms performed. And it turns out that the normal Holtz function with the exponential smoothing and the exponential trend outperformed the linear trend. And so that kind of is evidence of that, even though a lot of times the forecasts might look kind of weird because they're mostly flat. In fact, that ends up being a better representation of the smooth data in the short run than the linear method. That being said, if we were interested in creating an even longer forecast, and we maybe had a data set that over time wasn't situated between 2 points, and we weren't curious about like micro changes in the data, but maybe larger changes over time, then using the forecast linear method could be a better approach, because it would have an increased weight, apply increased weights for historical data. And so the other thing that you might notice too is that our forecast ends up almost identically following or lagging behind our actual temperature value. And this is actually as we expect, because every single time that we get a value in from standard in, we actually overwrite our past forecast. And so that's why it looks like our forecasts are trailing the actual data. But in reality, the real evidence that our forecasts here are different. And now you can see we're actually transitioning to the second beer, BV1. So in a short while, we should also see 2 forecasts associated with that once we've accumulated enough points in memory. So now that we've talked a little bit about what we're actually doing, let's go over and look at the code. So this is where I have my Telegraf agent running. And you can see it's outputting or printing the lines that we are creating, which include an anomaly in all of our forecasts. And it's very similar to the line protocol that Steven shared, but rather than keeping the data in a temperature measurement, we're keeping it in measurements entitled forecast, anomaly, and anomaly. I'm gonna get that right at some point. Linear. Anomaly. Anyways, so this is what our Telegraf config looks like. At the top here, we specify the configuration options for the agent, and we just set these to the default options. I will also mention, though, that we did set debug to true, and this is just a useful configuration option if you're unfamiliar with Telegraf or you have problems with Telegraf, so that you can get more error messages and try and figure out what's going wrong. So that's a useful command. And then here's our inputs Execd portion of our Telegraf config. So we are reading data from a text file, and we have 2 processors, and one configuration that we include is the name pass, which specifies that which data points you want to send to your Execd processor plugin. And in this case, since our forecasting Python scripts end up sending a lot of forecasting and anomaly data, we want to make sure to only pass in the raw temperature data to our forecasting script. So we tell the processor plugin to only pass in that data, and then we use the command option to specify how we want to run a Python script, and we use Python to call that script, and then we run it. And we do the same thing for our second forecasting script as well. Finally, we use the file plugin to send these metrics to standard out. And last but not least, we also use the InfluxDB v2 plugin to write our data to InfluxDB. So this is what our forecasting2.py script looks like. First, we simply import all of our dependencies. If you are a Python user, I can recommend this line protocol parser library to easily parse your time series data into a JSON object. And the first thing that we wanted to do was to define a mini batch length and a max batch length. And the idea here is that we want to start creating forecasts as soon as we possibly can. So as soon as we have 10 data points, we can start using Holt and stats models to create forecasts. But we also know that the more data we have, the more reliable our forecasts will be. So as soon as we get 10 points in memory, we'll start creating forecasts, but we'll allow that array to grow to 120 points. And as it does so, we'll continuously be outputting forecasts as well. So that just kind of gives us some more flexibility. And so the very first step is to take our data from standard in and to parse it using that InfluxDB parsing library. And then after that, I simply appended all of the fields that are relevant to me and the timestamps to separate arrays. And then after that, I joined them into one data frame. And the reason why I did that is because the stats models requires that you define your date time index with this method, just so that it can be aware of the interval between your timestamps, so that it can output future predictions with timestamps automatically. If you didn't want to do this, you could also auto-generate your own timestamps, or if you had a regular data, you could do it that way as well. We also ensure that that we have a complete batch length of data before we actually create a forecast. And this is valuable because this will also hopefully tell us that if we're not getting any forecasting data, or we're not getting any anomaly data, that that is an anomaly in and of itself. So I would suggest maybe setting up a dead man alert as well and monitoring whether or not you're not getting any data. And then we use the Holt function to fit our data. And this is the script for the linearly weighted trend version of Holt. So we set exponential to false. By default, it's true. And we use the estimated initialization method. You can also initialize some of the parameters for the algorithm manually if you want to make this even more efficient. And we make sure to also optimize the fit. And then we can simply call the forecast method and specify the number of predictions that we want to make. In this case, predictions is equal to 10. And create our predictions, and then we serialize that data and convert it back into line protocol just with some strings. And then we print those lines. And the forecasting pie is very similar. The only difference is the adjustments in the way that we are using the Holt function. So another thing I wanted to talk about was how it is that we actually built these scripts. So one thing to notice is that we're reading data in and we're creating forecasts onto the future. So in order to actually display forecasts forward in time, the syntax that you would do when building your Flux script is to specify that your data started. In our case, we were looking at data from 5 minutes ago. And to look at data into the future, you just specify the number of minutes in the future, and you don't need a +5 or anything because that's implied. So I also want to point out, this is an interesting example of where the anomaly linear perform as well as the exponential, because it's probably looking at the overall trend for a longer period of time, and its fast was probably way up here. So when all of a sudden this actual data dropped significantly, it calculated a bigger difference, whereas the exponential function was looking at the difference in slope between all of these points, which don't have a slope, have a slope of 0, and probably ended up having a much flatter line, which is what, so that's see such a difference in the anomaly here. And as a final step, I've been calling these anomalies the whole time, but really they're just a measure of the deviation or forecast in our actual value, or they're sort of like a residual. What I would probably do is take this one further and maybe use a flux task to create a threshold and decide that certain anomalous spikes above a certain value are true anomalies, and then just alert on those.
Okay, so some questions you might have. What are the advantages to running the Execd plugin as opposed to, say, a cron job? We do have a plugin that works more like a cron job. It's the inputs.exec plugin. If you have stuff that you need to run infrequently, that works okay for collecting metrics. In the case of processors that they typically need to respond really, really quickly, we see tens, hundreds, thousands, or tens of thousands of metrics per second, in some cases, and Telegraf needs to be able to go through each of those metrics really quickly. So like performing these in a batch operation, you're going to pay some startup costs to starting up an external process. So what Execd does is starts up the process once when Telegraf starts and just streams all the data back and forth between that process. So the actual cost for the per metric processing is really, really low. And you can see the number of metrics that were going by in the console window just a minute ago. And we're processing, I mean, we have about 1 metric per second, which is not a lot, but it's also, yeah, it's running 10 forecasts on the metrics that it sees going through. So it keeps a memory of what it's seen, it runs a forecast, generates multiple forecasts every second, and then writes those metrics out as well. So your ability to scale that up is a lot greater with a streaming kind of solution, and that's what the Execd is. Next question, can you use the Execd processor plugin in combination with a neural network? You can. I would think probably the best way to do that would be to train your neural network on a large data set and then bring the trained model over into an Execd process where you sample the data going through and run it against your trained model to do some predictions or classification. When shouldn't you use the Execd plugin? I suppose if you're writing something that's intended for a large audience, applicable to a lot of people, you might want to write it in Go and submit it to the Telegraf project. Otherwise, I think the Execd is a really good option to look at. What other streaming algorithms should I look into for, what other learning algorithms should I look into for streaming data? I'm going to pass this one over to you.
Yeah, so neural nets are definitely an option. I would add to what you were saying earlier that if you do want to use a neural net, it could be really advantageous to also calculate the residual. And if the residual exceeds a certain level, then that's when in the background you might be retraining your data on historical data at the same time. But like this question, I think ultimately depends on what you're trying to achieve. I also can recommend scikit multiflow if you are a Python user, That's a really awesome library for calculating or doing classification with streaming data. One other approach that we theoretically could have taken with this data, for example, is to try and categorize what irregular peaks look like, and just separate each, like a mini batch of data, and determine whether or not it exhibits the same shape as an irregular peak or not. Yeah, basically, and then also if you have enough data to train on, and you have seasonality, Facebook Profit is really easy to use and it's highly tunable. So I would also recommend giving that a try.
I have one more question to add.
Mm-hmm.
How did we rewrite all the timestamps on the data? Do you want to show that?
Yeah. Oh, right.
Yeah, so we glossed over it in the Telegraf config. There was a input Execd plugin, and yeah, right there at the top. And it's actually running a process called metric replayer and passing in our timestamp data. So if you go into the Explorer on the left and go to the metric replayer main.go, you can see the source code for it. It's not an overly large program. It's written in Go, and it reads in a metric file, a file with metric data, and then changes the timestamps to whatever interval that you want. And we did this so that we could replay this. It's actually multiple, like I don't know, a month of data, and we replayed it over the course of the talk. So that's interesting. It's in our repo, which we're going to share right now at the list of resources that you can follow up on.
Yeah, and similarly, if you want to run this for yourself, in the README, there are all the instructions, and the only thing you need to really do, other than build it, is to make sure to amend your temperature data with the current timestamp, so that when you play it, you can see it as a live demo like we are doing now. So these are the resources for this talk. The first one is the Telegraf repo. I encourage you to go there and give it a star if you do like Telegraf and you're a fan. Or if you have any ideas for an Execd plugin and you want a version, then please do. And then the second link is to the repo of our friend Luke, where this data came from. The third is the link to the repo that contains all this code for this talk. And the second to last link is the ORC that Luke used to read the temperature data from his analog temperature sensor. And last but not least, we have a link to InfluxLine protocol. If you are just getting started with Influx, this is a great place to start. Finally, I want to thank you all for coming to this talk, and I hope you enjoyed it. And if you have any questions at all about time series, about forecasting, about detection, about Telegraf, whatever it may be, I highly encourage you to check out our Discourse site as well as our Slack channel, and get in touch and share your thoughts. Thank you so much.
Thank you.